This video is about standing waves. Standing waves are different from traveling waves, and they have unique properties. Let's start by discussing how a standing wave forms. If I have a wave and it travels from left to right, and then this wave encounters a boundary, maybe this end is fixed right here, this wave will then reflect back on itself from right to left, and the wave traveling from left to right and the wave traveling from right to left will destructively and constructively interfere with itself to create a standing wave. The standing wave will appear to have the crests of the wave stay in one place, and points where the wave does not move at all will also stay in one place. One of the properties of a standing wave, or one of the points of a standing wave that's important to know about are called nodes. Nodes are points where destructive interference causes the displacement of the wave to be zero. You can see nodes formed in the wave above at the very end, here, 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 and here. It's important to note that the distance between two nodes is half a wavelength. Another point on a standing wave that's important to know about is an antinode. Antinodes are points of constructive interference. Antinodes occur halfway in between a pair of nodes, and at an antinode, the displacement of the particles is at maximum. You can see antinodes on the figure above here, 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 and here. Another important property of standing waves is that the points between nodes are in phase with each other, and the velocity is in the same direction. This means that if I have a standing wave that looks like this, between these two nodes, the string will vibrate back and forth like this. As the string vibrates back and forth, all the points between these two nodes, in this example here, are moving downwards like this. So they all have the same velocity downwards. The other property of a standing wave that's important to know about is that the points between the next set of nodes have the opposite velocity as the previous set of nodes. That means that if I look at my first two nodes, the velocity was going downwards, and if I look at the second two nodes between this node and this node, the velocity of all the points is going to be going in the opposite direction. So as this string vibrates back and forth, all of these points are going to be moving upwards with the same velocity, because the points in the previous set of nodes were moving downwards with the same velocity. The amplitude of the oscillation of the standing wave is different at different points. For example, if I look in between two nodes, the amplitude of oscillation at the nodes is 0. And as I progress toward the antinode, the amplitude of the oscillation increases until I reach the antinode, at which point the amplitude of the oscillation is at maximum. The last important thing to know about standing waves properties is that standing waves do not transfer energy the way traveling waves do. The energy of a standing wave is transferred one direction by one wave traveling from left to right, for example, and it's transferred in the opposite direction by another wave traveling right to left. So there is no energy transfer. The very last thing you have to understand about the properties of standing waves has to do with boundary conditions. And boundary conditions will determine whether or not an antinode or a node is formed. There are two types of boundary conditions. The first one is a fixed boundary. A fixed boundary could be something like the fixed end of a rope, or it could be something like the closed end of a pipe. Whenever a standing wave encounters a fixed boundary, it will create a node. So basically a fixed boundary always equals a node. And the reason for this is, if we look at a standing wave, if I have my wave starts here, travels, and it encounters a fixed boundary here. Remember what we learned about reflection. Whenever something reflects off a fixed boundary, it has a 180-degree phase shift. And whenever we have a 180-degree phase shift, that means that we are completely out of phase with the previous wave. So when I reflect back at this node that's formed at this fixed boundary, I have my wave coming in that is 180 degrees or pi radians different than the wave that is reflecting back. So you get a phase, so you always get a node at a fixed boundary. The other type of boundary is a free boundary, and you'll find these, for example, at the open end of a pipe. And whenever you have a free boundary, you'll create an antinode. So basically a free boundary is going to equal an antinode. So if I have a pipe, for example, I have a closed end on the left, an open end on the right. So I would create a node at the closed end, and at the open end, I would have an antinode. All right, that's it for the properties of standing waves.